Good day, everyone. Since you clicked this video, I assume that you're here to get some info about logarithmic functions. Well, don't worry, because we got you covered. Today, we will be exploring about the concept of logarithmic functions and delving into its properties, as well as learning about expanding and simplifying logarithmic functions and evaluating these functions. Hopefully, by the end of this video, we have made your learning experience a little more convenient and you will have received some guidance and idea about logarithmic functions. In mathematics, before the discovery of calculus, mainly math scholars used logarithms to change multiplication and division problems into addition and subtraction problems. In logarithms, the power is raised to some number to get some other number. Firstly, to ease our way into the topic, let us define what logarithmic functions are. In mathematics, the logarithmic function is an inverse function of an exponentation, also known as exponential function, where x is greater than 0, a is greater than 0, and a is not equals to 1, and is defined as logarithm of x to the base of a is equals to y. The base of the logarithm is a and can be read as logarithm of x to the base of a or logarithm to the base of a of x, and it is equivalent to a to the power of y is equals to x, and it is exponential form. Converting logarithms and exponential. Since logarithmic functions are the inverse function of an exponentiation for a first activity, let us try to convert exponential to logarithmic functions, and vice versa, respectively. Don't be stressed out when you find it a little confusing at first, as this is something that is better understood with visual aid rather than with words alone, but nonetheless, it is one of the simplest concepts of this topic. First, let us try converting exponential function to logarithmic function. For our first example, we have 2 cubes equals 8, which gives us the answer of logarithm of 8 to the base of 2 equals 3. To convert the exponential function, we have the logarithm of our answer, which is 8 to the base of 2 is equal to our exponent 3. We're essentially following the flow of how we read logarithm. And if you try to take a look at the logarithm, it adds 2 raised to what power will give us 8, and the answer to the logarithmic function is 3. Remembering, this question is a good guide when expressing exponential function to logarithmic functions. Also, always remember that our base is always stuck to the log symbol. Next example, we have 13 squared equals 169. So we have the logarithm of our answer. Here our answer is 169 to the base of 13 is equals to our exponent read as logarithm of 169 to the base of 13 equals 2. Simple, right? But if you feel like you need some more practice, don't worry. We have 4 examples to help your understanding. For our third example, we have 5 cubed equals to 125, which gives us the answer. Logarithm of 125 to the base of 5 is equals to 3. So just like before, we have the logarithm of our answer, 125 to the base of 5 is equals to 3. Next, we have 6 to the power of 4 is equals to 1,296. To convert it, we have the logarithm of 1,296 to the base of 6 is equals to 4. That is logarithm of 1,296 to the base of 6 equals 4. Great job! I think you guys are getting hang of it alright. For our last example, we have 10 squares equals to 100. Applying the steps, we got log 100 is equals to 2. You might be wondering, why does the log not have a base? Well, if there's no number attached in the symbol, it signifies that our base is 10. Just like when there is no number indicated in radical sign, the value is automatically 2. When no number is indicated in a log sign, then by default the base is 10. Alright, now that we have discussed expressing exponential to their logarithmic counterparts, it is now time to do the vice versa, converting logarithmic function to exponential. But don't worry, since it's just simple as the previous one. For example, logarithm of 169 to the base of 13 is equal to 2. Its exponential form would be 13 squared is equal to 169. So how did we get this answer? To convert logarithmic function to its exponential counterpart, the first thing to do is determine the base. And as I have said before, the base is always stopped to the log side. After we find the base, we must determine the exponent, which is the answer in the logarithm. And finally, we must find the product. We could also use the guide question to help us along. In this case, it would be 13 raised to the power of what will give us 169. That number is 2. Therefore, 2 will be your exponent. A pattern is also evident when writing the exponential. That is, you start with the base to go to your right, and from your right, you go to your left. Different methods work on different people. So, find one that works on you. Next, let us try logarithm of 64 to the base of 4 is equal to 3. In exponential form, it is 4 to the power of 3 is equal to 64. So we first find our base, which is 4, and determine our exponent, which is 3. Since it's the answer in the logarithm, and when we raise 4 to the power of 3, we get our product 64. You might check if your answer is correct by evaluating the function. Example number 3. Logarithm of 225 to the base of 15 equals 2. This time, let us try to use the pattern. So we start with our base, which is 15, go to the right, and we find 2, then we go to the left, and find 225, giving us 15 squared is equal to 225. By applying different tips on expressing logarithms to exponentials, we can express our last two examples. Logarithm 10,000 is equal to 4, and logarithm of 81 to the base of 9 is equal to 2. We get the answer 10 to the power of 4 equals 10,000, and 9 squared equals 81, respectively. Now, let us move on to the next concept, which are properties of logarithmic functions. Like in any other branch in math, properties are there to allow you to simplify complex equations or expressions. In this case, it is here to enable us to simplify logarithmic expressions. There are 8 properties of logarithmic function: product rule, quotient rule, zero exponent rule, power rule, identity rule, exponent rule, logarithm of a root, logarithm of a to the base of a to the power x is equal to 1 half x.
The first property is the product rule. Multiply two numbers to the same base, then add the exponents. The logarithm of a product is equal to the sum of the logarithms. Defined as the logarithm of mn to the base of a is equal to the logarithm of m to the base of a plus the logarithm of n to the base of a. For example, we have the logarithm of 8x to the base of 3 is equal to the logarithm of 8 to the base of 3 plus the logarithm of x to the base of 3. Next, we have the logarithm of 9 times 5 to the base of 3 is equal to the logarithm of 9 to the base of 3 plus the logarithm of 5 to the base of 3. The logarithm of dy to the base of 4 will be equal to the logarithm of t to the base of 4 plus the logarithm of y to the base of 4. The logarithm of mx to the base of 6 will now be equal to the logarithm of n to the base of 6 plus the logarithm of x to the base of 6. Lastly, we have the logarithm of 3 times 4 to the base of 8 is equal to the logarithm of 3 to the base of 8 plus the logarithm of 4 to the base of 8. Next, we have the quotient rule. Similar to the product rule, divide two numbers with the same base. Subtract the exponents. The logarithm of a quotient is equal to the difference of the logarithms, defined as the logarithm of m over n to the base of b is equal to the logarithm of m to the base of b minus the logarithm of n to the base of b. For example, the logarithm of 13 over x to the base of 5 is equal to the logarithm of 13 to the base of 5 minus the logarithm of x to the base of 5. The logarithm of 2 over 9 to the base of 4 is equal to the logarithm of 2 to the base of 4 minus the logarithm of 9 to the base of 4. The logarithm of s over d to the base of 5 is equal to the logarithm of s to the base of 5 minus the logarithm of d to the base of 5. The logarithm of 3 over x to the base of 9 is equal to the logarithm of 3 to the base of 9 minus the logarithm of x to the base of 9. The logarithm of x over y to the base of 9 is equal to the logarithm of x to the base of 9 minus the logarithm of y to the base of 9. Then we have the zero exponent rule. Any base that is the logarithm of 1 is equal to 0 because any number raised to the power of 0 is equal to 1. Defined as the logarithm of 1 to the base of a is equal to 0. Here are some examples. The logarithm of 1 to the base of 5 is equal to 0. The logarithm of 1 to the base of 21 is equal to 0. The logarithm of 1 to the base of 16 is equal to 0. The logarithm of 1 to the base of 8 is equal to 0. The logarithm of 1 to the base of 55 is equal to 0. Fairly easy, right? Now, let's move on to the next property. Next is the power rule. Raise an exponential expression to the power and multiply the exponent. Defined as the logarithm of m to the power of y to the base of b is equal to y times logarithm of m to the base of b. Here are some examples. The logarithm of 6 cubed to the base of 5 is equal to 3 times the logarithm of 6 to the base of 5. The logarithm of 21 squared to the base of 8 is equal to 2 times the logarithm of 21 to the base of 8. The logarithm of 9 cubed to the base of 16 is equal to 3 times the logarithm of 9 to the base of 16. The logarithm of 122 to the power of 7 to the base of 7 is equal to 7 times the logarithm of 122 to the base of 7. The logarithm of 44 raised to the power of 6 to the base of 6 is equal to 6 times the logarithm of 44 to the base of 6. The next property is the identity rule. When taking the logarithm of something to the base of the same thing, the logarithmic expression is simply equal to 1, because any number raised to the power of 1 is equal to the number itself. It is defined as the logarithm of a to the base of a is equal to 1. For example, we have the logarithm of 13 to the base of 13 is equal to 1. The logarithm of 24 to the base of 24 is equal to 1. The logarithm of 7 to the base of 7 is equal to 1. The logarithm of 10 is equal to 1. The logarithm of 4 to the base of 4 is equal to 1. So that was 5 down and 3 more to go. For the next property, we have the exponent rule. When there is an exponent on the term within the logarithmic expression, and that term is the same as the base of the logarithm, the answer is simply the exponent. It is defined as the logarithm of a raised to the power of b to the base of a is equal to b. For our first example, we have the logarithm of 3 raised to the power of 4 to the base of 3 is equal to 4. The logarithm of 15 raised to the power of 8 to the base of 15 is equal to 8. The logarithm of 4 raised to the power of 33 to the base of 4 is equal to 33. The logarithm of 12 raised to the power of 17 to the base of 12 is equal to 17. And the logarithm of 8 raised to the power of 9 to the base of 8 is equal to 9. The next property to discuss is the logarithm of roots, which is defined as the logarithm of the nth root of b to the base of a is equal to the logarithm of b to the base of a over n. For example, we have the logarithm of the fourth root of 5 to the base of 2 is equal to the logarithm of 5 to the base of 2 over 4. The logarithm of the cube root of y is equal to the logarithm of y over 3. The logarithm of the z root of 7 to the base of 9 is equal to the logarithm of 7 to the base of 9 over z. The logarithm of the y root of 6 to the base of 11 is equal to the logarithm of 6 to the base of 11 over y. Finally, the logarithm of the cube root of 8 to the base of 12 is equal to the logarithm of 8 to the base of 12 over 3. And lastly, the property we will be talking about next is the logarithm of a to the base of a raised to the power of x is equal to 1 over x, and it is defined as the logarithm of a raised to the base of a raised to the power of x is equal to 1 over x. Here are some examples. The logarithm of 4 to the base of 16 is equal to 1/2. That is because 16 is 4 squared. Next, we have the logarithm of 5 to the base of 3125 is equal to 1/5. That is because 3125 in exponential form is 5 raised to the power of 5. Next, we have the logarithm of 6 to the base of 216 is equal to 1/3. And you've guessed it, 216 in exponential form is 6 raised to the power of 3. Next, we have the logarithm of 2 to the base of 128 is equal to 1 over 7. Then lastly, we have the logarithm of 8 to the base of 64 is equal to 1/2.
Now that we have discussed the different properties of logarithmic functions, let us now proceed to the next subtopics, which are the expanding logarithmic and converting logarithmic expression into single logarithm. Let us first start with the expanding logarithms. When you are asked to expand log expression, your goal is to express single logarithmic expression into many individual parts or components. This process is exact opposite of condensing logarithm, because in condensing, you compress a bunch of log expression into simpler one. The key to successfully expanding logarithms is to carefully apply the rules or properties of logarithms. Take time to go over the rules and understand what they are trying to say. Now let us try to expand the following logarithmic functions. First, we have logarithm of 3xyk to the base of 5. In expanded form, it becomes logarithm of 3 to the base of 5 plus logarithm of x to the base of 5 plus logarithm of y to the base of 5 plus logarithm of k to the base of 5. As I have said, the key to successfully expanding logarithms is to carefully apply the rules of logarithms. Looking inside the parentheses, we see a product of a number and variables. Thus, we follow the product rule, so we'll separate the main log expression, a sum of 4 logs. Next, we have logarithm of 7x over y to the base of 2. The inside of the parenthesis is a fraction, which means that we'll first apply the quotient rule. Since the numerator is a product of 7 and x, the product rule will break it up. The same rule applies as well if it were the denominator. So, the expanded form would be logarithm of 7 to the base of 2 plus logarithm of x to the base of 2 minus logarithm of y to the base of 2. For a third example, we have logarithm of 2v squared times y cubed. Inside the parentheses, we see the product of a number and variables, that we have exponent. Therefore, we follow two rules, the product rule and the power rule. So in expanded form, we have logarithm of 2 plus 2 logarithm of v plus 3 logarithm of y. Next, Let us try an example that incorporates the logarithm of a root. Let us try to expand the expression of logarithm of square root x to b over 3. Similar with the other example, we apply the properties of a logarithm. Here we have the product rule, quotient rule, and the logarithm of root. So in expanded form, our answer is equal to logarithm of x over 2 plus logarithm of 2 plus logarithm of t minus logarithm of 3. Alright, let us now proceed to our last example. We have logarithm of a squared b squared over square root of e to the base of 8. The properties found in this function are the same as previous example, but this also includes the power rule. So in expanded form, we have 2 times logarithm of a to the base of 8 plus 3 times the logarithm of d to the base of 8 minus logarithm of e to the base of 8 over 2. Great job, everyone! We are now halfway through our topic. I know it's quite a lot to grasp in just a few minutes, but with more practice, you'll be good in no time. Now let us proceed to the next part, which is converting a logarithmic expression into single logarithm. In condensing a logarithm, the process is just the opposite of expanding logarithms, but similar to expanding logarithms. The key to successfully condensing logarithms is to carefully apply the rules of logarithms. For our first example, let us try to condense the expression 2 log x minus 4 log x plus 5 plus 1 over x log 3x plus 5 into a single logarithm. Firstly, we have to determine the properties that could be applied. Here we have the product rule, the quotient rule, and the power rule. In converting, we apply the power rule first, then apply the product rule to sum. Finally, we apply the quotient rule to the difference. So in the condensed form, it is log x squared over x plus 5 to the power of 4, 3x plus 5 to the power of 6, negative 1. For our next example, we have logarithm of 2 to the base of 6 plus 2 logarithm of a to the base of 6 plus 3 logarithm of b to the base of 6 minus logarithm of c to the base of 6. So the rules we apply here are the same with the previous example. The power rule, the product rule, and the quotient rule. And just like before, we apply the power rule, power rule first, followed by the product rule, then lastly the quotient rule. So our answer is logarithm of 2 a squared b cubed over c to the base of 6.
Example number 3. 4 times the logarithm of v to the base of 2 plus the logarithm of x to the base of 2 over 3 minus 5 times the logarithm of y to the base of 2 minus logarithm of z to the base of 2. Just like before, we determine the rules and apply them. Therefore, its condensed form is the logarithm of v raised to the power of 4 times the cube root of x over y raised to the power of 5 times z to the base of 2. Example number 4 is logarithm of x plus 4 to the base of 3 plus 4 times the logarithm of x plus 3 to the base of 3 minus 6 times the logarithm of y to the base of 3. Apply the steps and we get the logarithm of x plus 4 times x plus 3 raised to the power of 4 over y raised to the power of 6 to the base of 3. For our last example, we have 4 times the logarithm of c minus 2 times the logarithm of c plus 7 minus 3 times the logarithm of c over 4. Using the same steps and methods with the previous examples, the answer will be the logarithm of c raised to the power of 4 over c plus 7 squared times the fourth root of c cubed.
Next, let us proceed to evaluating and simplifying logarithmic expression by applying the different properties of logarithms. When evaluating and simplifying log expression by applying the different properties of logarithm, we must take note of the following. First, keep the constants, only focus on the logarithms. Determine the rule applied, and lastly, simplify the expression to get the answer. For our first example, we have 3 logarithm of 2 to the base of 2 plus logarithm 16 to the base of 4. So as we said, the constants remain and focus on the log expression. The rules to be used here is the identity rule and exponent rule. So following the rules, logarithm of 2 is to the base of 2 is equal to 1 and logarithm 16 to the base of 4 is equal to 2. With that, we have 3 times 1 plus 2, then we simplify, therefore our final answer is 5. For our second example, we have 4 logarithm of 1 to the base of 3 minus logarithm of 10. So like before, let us determine the rules to be applied. Here we have the zero exponent rule and identity rule respectively. Next, we apply the rules. It turns our expression into 4 times 0 minus 1. After that, we simplify. Therefore, our answer is equal to negative 1. Example number 3. We have logarithm 243 to the base of 3 over 5 plus 5 logarithm of 100. Again, only focus on the logs and let the constants be. As we can see, the rule present here is the exponent rule. With that, when we apply the rule, our expression becomes 5 over 5 plus 5 times 2. So 5 over 5 equals 1 and 5 times 2 is equals to 10. So now our expression is 1 plus 10. After that, we simplify, then we get 11. Therefore, our answer is 11. For example number 4, we have logarithm 2 to the base of 4 minus logarithm 1 over 2 and logarithm 7 to the base of 7. The same as the other example, the constant will remain and we will determine the rules. The rules here are the logarithm of a 2 if a to the base of ax is equals to 1 over x, zero exponent rule, and identity rule. After applying the rules, we now have 1/2 minus 0 over 2 plus 1. When we simplify it, we will have 1/2 minus 0 plus 1. Then when we simplify again, we get our answer, which is 3/2. And for our last example, we have 7 log 8 to the base of 8 plus 2 log 27 to the base of 3. Again, let the constants be and determine the rules. The rules we have here are identity rules and exponent rule. After applying the rules, we have 7 times 1 plus 2 times 3. We then simplify the terms, which give us 7 plus 6. Simplify again, and we have reached the final answer, which is 13. That wasn't quite so hard, right? Now, let us proceed to our last subtopic. Finally, for the last subtopic, we will be discussing about solving logarithmic expression. A logarithmic equation is an equation that involves the logarithmic of an expression containing a variable, and the purpose of solving a logarithmic equation is to find the value of the unknown variable. Logarithmic equation may be divided into two types: equation with logarithm on one side and equation with logarithm on both sides. Both have similar solving methods with just slight differences. How do we solve equation with logarithms on one side? Here are the steps. First, simplify the logarithmic equation by applying the appropriate laws of logarithms. Next, rewrite the logarithmic equation in exponential form. Then now simplify the exponent and solve for the variable. And lastly, verify your answer by substituting it back in the logarithmic equation. You should note that the acceptable variable of a logarithmic equation only produces a positive argument. Now, let us practice on the following example. Example number 1. So, logarithm 5x plus 7 to the base of 2 equals 5. Since it's already a single logarithm, we'll rewrite the equation in exponential form, so it becomes 2 to the power of 5 equals 5x plus 7. Then we'll simplify the equation. Is equals to 32. 32 equals 5x plus 7. 5x plus 32 minus 7. 5x equals 25. Lastly, we divide both sides by 5 to get x. Therefore, x equals 5. Example number 2. Solve for x in log 5x minus 11 equals 2. Since the base of this equation is not given, we therefore assume the base of 10. Then we change the expression in exponential form. Now we have 10 squared equals 5x minus 11, and it becomes 100 equals 5x minus 11. Lastly, we simplify to get our x, so we have 111 equals 5x divided by both sides by 5. Hence, x equals 111 over 5 is the answer. For our third example, solve logarithm 2x plus 1 to the base of 10 equals 3. Same as before, we write the equation in exponential form. It then becomes 2x plus 1 equals 10 cubes. Then we simplify, so it is now 2x plus 1 equals 1000. Transpose the 1 and simplify, and we get 2x equals 999. On dividing both sides by 2, we get x equals 499.5. You may verify your answer by substituting it in original logarithmic equation. Example number 4. Solve for x if logarithm of x the base of 4 plus logarithm of x minus 12 to the base of 4 equals 3. First, simplify the logarithm by using the product rule as follows. So now it becomes logarithm of x times x minus 12 to the base of 4 equals to 3. Then distribute the x, giving us logarithm of x squared minus 12x to the base of 4 equals 3. Next, convert the equation in exponential form. 4 cubed equals 6 squared minus 12x. Simplify and we get 64 equals x squared minus 12x. We will equate it to 0 and we form a quadratic equation. Since this is a quadratic equation, we therefore solve by factoring. The factors x squared minus 12x minus 64 are 4 and minus 16, negative 16. To get our x, we must equate it to 0, giving us x plus 4 times x minus 16 equals to 0. So x equals negative 4 or 16. But when x is negative 4 is substituted in the original equation, we get a negative answer which is imaginary. Therefore, 16 is the only acceptable solution. For our last example, we have solved the logarithmic equation. Logarithmic x plus 1 to the base of 2 minus logarithmic x times x minus 4 to the base of 2 equals 3. First, simplify the logarithms by applying the quotient rule as shown below. Now we have logarithm times x plus 1 over x minus 4 to the base of 2 equals 3. Now rewrite the equation in exponential form. 2 cubes times x plus 1 over x minus 4, and simplify the exponent. 8 equals x times x plus 1 over x minus 4. Then cross multiply the equation, we get x plus 1 equals 8x minus 4. X plus 1 equals 8x minus 32. Transpose and combine like terms. We have 7x is equal to 33. Divide both sides by 7, and our x is 33 over 7. Now, let us proceed to the procedure of solving equation with logarithms on both sides and equal sign. If the logarithm have a common base, simplify the problem and then rewrite without logarithm. Simplify by collecting like terms and solve for the variable in the equation. Check your answer by plugging it back in the original equation. Remember that an acceptable answer will produce a positive argument. Without further ado, let's practice on following examples. For our first example, solve logarithm of 2x minus 4 to the base of 6 plus logarithm of 4 to the base of 6 equals logarithm of 40 to the base of 6. First, simplify the logarithms. So, we have logarithm of 4 times 2x minus 4 to the base of 6 equals logarithm of 40 to the base of 6. Since we have the same base, we drop the logarithms, making it 4 times 2x minus 4 equals 40. Distribute the 4, which will give us 8x minus 16 equals 40. Then transpose. It will become 8x equals 40 plus 16. And add like terms. Now we get 8x plus 56. Divide both sides by 8 and we get x equals to 7. Next equation we have to solve is the logarithmic equation, logarithm x minus 2 to the base of 7 plus logarithm x plus 3 to the base of 7 equals logarithm times 14 to the base of 7. Our solution will be to first simplify the equation by applying the product rule. So now it is logarithm x minus 2 times x plus 3 to the base of 7 equals logarithm of 14 to the base of 7. Same base, so we drop the logarithms and it becomes x minus 2 times x plus 3 equals 14. Apply the FOIL method to get x squared minus x minus 6 equals 14 when we turn it into quadratic equation, which gives us x squared minus x minus 20 equals 0. So in order to acquire x, we need to factor the equation. So here our factors are 4 and negative 5. And in order to get x, we need to equate it. So 0 and so x times x plus 4 times x minus 5 equals 0. Now our x is equals to negative 4 or 5. When x is equals to negative 4 and x is equals to 5 are substituted in the original equation to give a negative and positive argument respectively. Therefore, x is equals to 5 and is the only acceptable solution.
For our third example, we have to solve the equation logarithm of x to the base of 3 plus logarithm of x plus 3 to the base of 3 is equal to the logarithm of 2x plus 6 to the base of 3. So let us solve. So first we express the logarithm into a single logarithm, giving us logarithm of x squared plus 3x to the base of 3. Now the equation is the logarithm of x squared plus 3x to the base of 3 is equal to logarithm of 2x plus 6 to the base of 3. Drop the logarithms to get x squared plus 3x equals 2x plus 6. Equate it to 0 and it turns to x squared plus 3x minus 2x minus 6 equals 0. Add the like terms and we get the quadratic equation x squared plus x minus 6 equals 0. Factor the quadratic equation to get x minus 2 times x plus 3 equals 0. So we have our x's, which is x is equal to 2 and x is equal to negative 3. By verifying both values of x, we get x equals 2 to be the correct answer.
For our fourth example, we have logarithm of x to the base of 3 plus logarithm of x minus 2 to the base of 3 equals logarithm of x plus 10 to the base of 3. Start by condensing the log expression on the left into a single logarithm using the product rule. What we want is to have a single log expression on each side of the equation. So first we apply the product rule. We have logarithm of x times x minus 2 to the base of 3 equals logarithm of x plus 10 to the base of 3. Then simplify by distributing x. Now, it is logarithm of x squared minus 2x to the base of 3 equals logarithm of x plus 10 to the base of 3. Then we drop the logs, set the arguments which are stuffed inside the parentheses, equal to each other, and we get x squared minus 2x equals x plus 10. Just like what we did to the other examples, we turn it into a quadratic expression. So we get x squared minus 3x equals 10 minus 10 equals 0, and solve the quadratic equation using the factoring method. We now get x minus 5 times x plus 2 equals 0. Set each factor equal to 0, then solve for x. So our x is 5 and negative 2. But when we substitute this value to our original equation, only 5 will give us positive answer. So therefore, 5 is our final answer. For our last example, we will solve logarithm x plus 2 to the base of 2 plus logarithm 3 to the base of 2 equals logarithm 27 to the base of 2. Since we want to transform the left side into single logarithmic equation, then we should use the product rule in reverse to condense it. Firstly, let us apply this product rule, so it becomes logarithm x plus 2 times 3 equals to the base of 2 equals logarithm 27 to the base of 2. Distribute 3 to simplify, giving us logarithm 3x plus 6 to the base of 2 equals logarithm 27 to the base of 2. Then we shall drop the log, which give us 3x plus 6 equals 27. Then we transpose and add like terms, so we have 3x equals 21. Divide both sides by 3, thus giving us the answer x equals 7. Now that we are almost finished with our discussion, a proper way to end it would be a short recap and summary. So now let us try to refresh our memory and see an overview of what we have learned today. Remember, in mathematics, the logarithmic function is an inverse function of exponentation, also known as an exponential function, where x is greater than 0, a is greater than 0, and a is not equal to 1, and is defined as logarithm of x to the base of a equals y, which can be read as logarithm of x to the base of a, or logarithm to the base of a of x, and is equivalent to a to the power of y, is equals to x in its exponential form. Again, to convert an exponential function to a logarithm, we are essentially following the flow of how we read logarithms and follow the guide question. And always remember that our base is always tucked to the log symbol. For logarithm to exponential, it is merely the opposite. The next concept, which are properties of logarithmic functions. Again, there are 8 properties of logarithmic functions: product rule, quotient rule, zero-exponent rule, power rule, identity rule, exponent rule, logarithm of root, logarithm of a to the base of a. This power of x is equals to 1 over x. In expanding logarithm, your goal is to express a single logarithmic expression into many individual parts or components. The key is to successfully expand the logarithms is to carefully apply the rules or properties of logarithms. When converting a logarithmic expression into a single logarithm, the process is just opposite of expanding logarithms, but similar to expanding logarithms. The key to successfully condensing logarithms is to carefully apply the rules of logarithms. When evaluating and simplifying a logarithmic expression by applying the different properties of logarithms, we must remember to focus on logarithms and let the constant be when we determine the rules applied to successfully gain our answer. And for the last one, solving logarithmic expression, a logarithmic equation is an equation that involves the logarithm of an expression containing a variable, and the purposes of solving logarithmic equation is to find the value of the unknown variable. Logarithmic equation may be divided into two types: equation with logarithms on the one side and equation with logarithms on both sides. Both have similar solving methods with just slight differences. We have finally reached the end of our mini math session. That would be it for now, and hopefully you have gained some ideas about the concept of logarithmic expression. Also, special thanks to my fellow members who took part in making this happen. So that's it for now. See you next time. Bye!